Now let's deal with an example of aircraft structures. It is actually a problem comes from McCann 3650 aircraft structures. I simplify this problem such that it is suitable for you to deal with. A thin wall can deliver with walls of constant thickness T has the cross-section shown in the figure. It is loaded by a vertically upward force W at the tip and a vertical downward force 2W at the midsection. Both forces acting through the shear center, which means there is no torsional effect in this beam. You are required to mathematically show that the centroid of the cross-section lies in the middle of the enclosed rectangle, as well as find the second moment of inertia, Ixx, Iyy, and Ixy of this cross-section. You need to determine and sketch the distribution of direct stress along the length of the beam for the points 2 and 3 of the cross-section. Notice that here we denote axial stress by using sigma C instead of sigma x, because we have a lot of sectional properties needed to be dealt with. Besides, ignore relatively very small terms for ease of calculation. Suppose t is very small in comparison to d. Firstly, let's show that the centroid of the cross-section lies in the middle. Firstly, we suppose we don't know where is the x and y coordinate system. We don't know where the centroid is. Therefore, we set up the x prime and the y prime coordinate system such that we can find the first moment of inertia of this cross-section first. Since it is a composite cross-section, we can just express the first moment of inertia in terms of the summation form. So the first moment of inertia about the y prime axis is given by the first moment of inertia of 1, 2, the first moment of inertia of 3, 4, the first moment of inertia of 2, 4, and the first moment of inertia of 1, 3. Then we substitute the average of x of 1, 2 as well as the area into the formula. The average value of x is d over 4 for 1, 2, d over 4 for 3, 4, 0 for 2, 4, and the d over 2 for 1, 3. The area of 1, 2, and 3, 4 are both Td divided by 2, where the area for 2, 4, and 1, 3 are both Td. The first moment of inertia of this rectangular cross-section about the y prime axis is given by 3Td squared divided by 4. Similarly, for the first moment of inertia about the x prime axis, it is given by 3Td squared divided by 2. Consequently, the average value of x and y are found to be d over 4 and d over 2 respectively, where it is just the position of the centroid. That is, the centroid lies in the middle of the rectangular cross-section. Now let's find the second moment of inertia, Ixx, Iyy, and Ixy of the cross-section. For Ixx, it is the integral of y squared dA over the entire region A. It is 2 times I12 plus I13. It is because I12 equals to I34 and I13 equals to I24. For I12, it equals to t cubed because since we are talking about y squared dA, then we talk about the thickness, which is in the vertical direction, will be cubed, and its length is d divided by 2. So its moment of inertia about itself is given by t cubed times d divided by 2 divided by 12. Besides, the area of 1, 2 is Td divided by 2, while the distance of 1, 2 from x-axis is given by d over 2. So by parallel axis theorem, we can find another term of moment of inertia about x-axis. For 1, 3 and the 2, 4, they are rather similar. They are both Td cubed divided by 12. Then we simplify and organize the terms to get this, but as what we mentioned, t is very small in comparison to d, therefore we can neglect this term to be 0. The final answer for moment of inertia of Ixx is 5Td cubed divided by 12. For Iyy, it is rather similar, but in this case, we don't need to apply the parallel axis theorem for 1, 2 and 3, 4. Instead, we apply the parallel axis theorem for 1, 3 and 2, 4. For 1, 2, since it's talking about x squared dA, then this length is taken into consideration and to be cubed. Since it is d over 2, then we have d over 2 cubed here. Then we times t. Besides, for 1, 3, still compute the moment of inertia of itself. It is given by t cubed d divided by 12. However, by parallel axis theorem, there is another term which is Td divided by d over 4 squared, where d over 4 is the distance of 1, 3 to the y-axis, as shown here. Reorganizing the terms and simplify it to get this. Finally, since t is very small in comparison to d, then we neglect this term to get Iyy equals to 7td cubed divided by 48. For rectangular cross-section, for Ixy it is very simple, since the cross-section is thinward rectangular, which is axially symmetrical. That means the moment of inertia of xy dA over the entire region A equals to 0 by empirical manner. Now let's determine and sketch the distribution of direct stress along the length of the beam for different points. First of all, we determine the moment inside the spar. Consider this simplified schema, 2W force in the middle and a W at the tip. By statics, we can immediately find the reactions at A. There is a moment MA as well as a shear force VA. Then by statics, take the moment at point A gives MA plus 2W times L over 2. L over 2 is the arm of 2W, minus W times L. L is the arm of W. So eventually you will get the result, which means the moment at point A equals to 0. Besides, for the shear force, assume an upward shear force. Then we found the shear force at point A, which is the reaction at point A, equals to W. Now we try to cut this cross-section, and we keep the right section for analysis. The sign convention of right section is like this. We take the moment here, then we can compute mx as well as v. However, under the pure bending case, we don't need to find v because the direct stress inside the beam is just caused by m. Therefore, we just find the moment in terms of se. mx equals to w se because for the upward force w, it has an arm of L minus se, while for the 2w force, it has an arm of L divided by 2 minus se. Therefore, by writing the moment equilibrium equation, we can get mx equals to w times se. Next, we consider the right section located here. So now the 2W force is disappeared as we propagate along the z direction. Mx is given by W times L minus se, where L minus se is just the arm of the moment. Now we can express m in terms of se, and we apply the equation sigma equals to my divided by I. Then we can have this result. Now let's consider point 2. At point 2, y2 equals to d divided by 2. Then we substitute y equals to d over 2 into the equation to get this result. Then, as you can observe, all those stuff are just linear to se. Therefore, the stress distribution along the length of the beam will still be linear. Consequently, we try to find the stress in the midsection, which is minus 3WL divided by 5TD squared. And then we connect those lines together to get the distribution of direct stress. For point 3, which is here, y3 equals to minus d over 2. Then you substitute into the equation to get this. Also, you find the direct stress in the midsection such that you can draw this distribution. Notice that when we substitute in the numbers, we also take this one into the consideration. So it is the original problem comes from our homework in Mechan 3650 aircraft structures. It is for your interest, and if you have time, you may want to try out this problem by adopting this advanced equation.